very grateful to David Rydh, who agreed to give this talk on a short notice. So his title is Milnor excision of stacks, pushouts, and etale, I think, neighborhoods. Please, David.
Yes. Okay, so thanks for giving me the opportunity to talk here. And perhaps etale here, I mean, we can also like smooth neighborhood. So anyway, so let's start with some basic definitions. And we'll start with a Cartesian square of rings. Let's say discrete, just ordinary commutative rings. And I'm going to keep the following notation. So the horizontal maps are going to be surjections from A to A naught and B to B naught. Yeah, so as I said, the first condition is that the horizontal maps are surjective. And the second condition is that it's a Cartesian square. So that A is the product of A naught and B or B naught. And as is well known, so this implies that that it's also co-Cartesian. So B naught is isomorphic to B tensor A naught. But note here, this is non-derived. So it's important here that it's an ordinary tensor product. So usually these Milnor squares are not co-Cartesian as derived rings on the level of pi naught. And of course also, I mean, the kind of this being Cartesian is just saying that the ideal of this surjection is isomorphic to the ideal of this surjection. So the kernel of A to A naught maps surjectively onto the kernel of B to B naught. Right, and there are a few special cases. I mean, I'm more or less going to treat the full general case, but there is still some interesting special cases that have been used more often than others. So one of these are the case where these surjections have nilpotent kernel. Let me perhaps call this I, which is important in deformation theory. So for example, the Schlesinger criterion for pro-restability of a functor involves Milnor squares where this is a nilpotent, where the kernel of this is nilpotent, and this is almost surjective. It's surjective up to some nilpotency. And the second important case is where B is a finite A module. So geometrically, these are sometimes called pinchings. And kind of also a special case of this is when we take B as the normalization of A. And we take I as the conductor. Also, right. And one can, in principle, treat any finite birational map factoring through a surjection followed by injection and make both those two into Milnor squares and deduce some results for general finite birational maps.
The conductor, does that mean the discriminant?
So the conductor here is the largest ideal inside A that remains an ideal inside B. So that I is isomorphic to IB. That's the classical. So that's exactly what's necessary to make it a Cartesian square. And then there's an even, well, perhaps that should have been in between here. Let me switch the order of these two. So a middle, well, okay, well, anyway, I think this makes more sense. That's the case when A to B is also surjective. So then we have a square with two surjections, or all four maps of surjections, and geometrically this means that you are gluing two closed subschemes, and I think these are sometimes called clutchings. Whereas, I mean, so here you can, for example, think of, let's say, take a P1 or a line and take 2 points, and then we pinch these 2 points together and we get a nodal curve. This is the spec of corresponding Cartesian square of commutative rings. Right, and also a warning here is that except for in the case 2 and 3, I mean, except in general, say A is rarely Noetherian. So even if you start with A naught and B naught and B Noetherian, the fire product is rarely Noetherian. In this case, and also, then of course also in this case, it is if everything is a finite type over some Noetherian base. Okay, so these are our Milnor squares. Then we come to excision. So, and I guess in uttermost generality, we would have a functor taking values in infinity categories. So let's phrase this. So let's see, be a functor from rings to infinity categories. But mostly, I mean, I'm going to talk about algebraic stacks later, and then it's going to be groupoids or perhaps high groupoids. But like if you take K-theory, you would have take values in spaces or spectra. And we say that this functor, okay, functor C satisfies Milnor excision if I have a Milnor square and I apply C, I get a homotopy pullback. Sometimes I have this problem that my pen is not picking up. It's very, it happens sometimes, and I never understand. It usually goes away when I move the pen, etc. So this should be if that is homotopy Cartesian. And yeah, I'm not super good at the history here, but I mean, I think it, well, as the name suggests, it is at some point due to Milnor, and also to Bas, and I also see many Murphy being mentioned here. So in the late 60s, where the easiest first case is that excision holds for vector bundles. For yeah, let's say let me call it Proj or VB, so finitely generated projective modules. And also, I mean, also back in the same papers, also proving that excision holds not for the whole K-theory, but for K-theory up to a degree at most 1, including negative K-theory. But it's false in general. And I think, I mean, there's also this result that there cannot be any kind of functor making it true. I think that's due to Swan. But if you instead do homotopy K-theory, well, then it does hold. I believe it's due to Jack Weibel. Right. So excision for KH. And then, I mean, the last few years, there has been these very nice results really extending this, understanding what happens for K-theory, and not just for homotopy K-theory. So there's the first paper of Kurs, Strunk, and Damme, which was published 2 years ago, which shows that excision does not hold, we know that. But if we do pro-excision, so let me just say this in words. So we have this surjection from A to A naught, and we can look at the infinitesimal neighborhoods of A naught in A, so A mod. I can write it here at the side. So if we let, so A naught is A mod I, and we can look at the infinitesimal neighborhoods, A mod I n plus 1. And then the pro-excision parts has to do with replacing, in this case here, the objects just over A naught with the limits of objects over all the infinitesimal neighborhoods. And it's a little bit more complicated in that, like if you take the K-theory, you don't get quite a, as I understand it, a Cartesian square of pro spectra, but some kind of weak square where you only get equivalences on the level of homotopy groups. Oh yes, see my pen is not cooperating properly. And more recently, also by Tamme and Marcus Land, I think this was published last year. I mean, they made up this nice general framework, kind of explaining. I mean, it's all due to this problem of this not being a derived pushout square. If it would be a derived pushout square, we would have a homotopy pullback of perfect complexes, and we would have, from the fact that K-theory is localizing, we would have excision for K-theory, but it's not. But they replaced the ring B naught with this circled dot product, explaining this failure, and use this to deduce kind of similar pro-excision results for other invariants. Yes, and as written in the chat, there's also other results on pro-excision, etc. Earlier, this is just there's many more results, but I think these are really landmark papers. So let's say for localizing invariants. It usually isn't this bad, but you have to bear with me. Right, and then you can also see that, I mean, the difference between between these two categories. So, okay, they of course vanish if these are equal. So if you have truncating invariance, we get excision on those. Let me also mention a few more recent papers. So there's this 2 recent papers from this year. I'm getting crazy about this. It wasn't this bad yesterday. So by Eldenamanto, Mark Hoyot, Iwasa, and Kelly. So where they study excision for CH sheaves. So they give a criterion for so a criterion for excision for CH sheaves. And in the second paper, they also prove that you do have excision for motivic multiple theory. Right, but yeah, so what I'm going to talk about are not CDH sheaves. But before that, I need a final result that is about CDH sheaves, and that's well, oh yeah, I guess this should probably come before. Anyway, this is an older paper. So here they prove that you have excision for arc sheaves. And an example of arc sheaves, always like etale cohomology, or just the category of sheaves or sets. And I'm going to use this later. Yes, and let me perhaps also mention a paper that's still not available as far as I know, by Tom Bachmann, Adil Khan, Sharanya Ravi, and Vladimir Sosnilo. So I don't know if perhaps some of them are here and can, perhaps it is now available, I don't know. Anyway, so probably next week. Okay, so so here, I mean, this is like a categorified version of Landhamme. So instead of working with Milnor squares of rings, they work with Milnor squares of idempotent complete stable infinity categories. Right. Yeah, and perhaps, I mean, I haven't mentioned this, but yeah, so here I'm focusing on Milnor excision, but of course, the one of the main motivations behind this is that you can combine Milnor excision for, let's say, for finite A to B plus, let's say, derived blowups to deal with abstract blowup squares. So proving pro-excision, let's say, pro-excision, for these cases, you can say something about excision for abstract blowups and being a CDH sheaf, which I think was the main motivation behind at least this paper. All right, but let's go to the main results for this talk. which is Milnor excision for algebraic stacks. And I said, when these are stacks are typically not or never CDH sheaves, so this kind of falls outside some of these. And okay, yeah, just for notational sake, I'm going to now work instead with Milnor squares of affine schemes or even stacks. It's very little difference. So let me again define a Milnor square just to get the notation set of algebraic stacks. And here you can work with one stacks if you like, but you could also work with higher geometric stacks. So here a Milnor square is a diagram. And I'm going to use the notation x naught x. So again, the horizontal maps are closed motions here. And with some arbitrary maps in the vertical direction, or almost not quite arbitrary. Yeah, so this is perhaps for the first condition, is that the vertical maps are affine. And the second condition is that horizontal maps are closed motions. And then we would like to, and then it's the Cartesian property. And whereas we know that the five product of rings by definition is, so that is Cartesian in the category of rings. So we would like to say it's co-Cartesian, but since we don't know yet even that the Cartesian square of rings is co-Cartesian when you take the spec in the category of stacks, I'm instead going to just force that on the level of functions, it is a push-out. So the precise condition here is that the structure sheaf of Y, which would be the pullback if it would be rings, should be isomorphic to the five product of OX and OY naught over OX naught. But of course, I also need to push these so it makes sense. So F lower star OX I lower star, F lower star, and J lower star. So, and as you can see, I mean, this condition is local on Y for, let's say, the flat topology. Five products are preserved by flat base change. Being affine is also a local question, and being a closed motion is also a question. So you could say that these conditions are just equivalent with saying that, let's say, flat or smooth locally on Y, it is a Milnor square of affine schemes. So this is a natural definition. And also, as before, we know that Milnor squares are they are Cartesian, even though they're not Cartesian. Well, so in a ring case, they are co-Cartesian, but here they are Cartesian. So Milnor squares are Cartesian, but not derived Cartesian. So if you would like to do this for derived stacks, the right condition here will, we would say that that it's Cartesian on the level of classical stacks, but not on the level of derived stacks. Right, and another interesting thing is that they are co-Cartesian on the level of topological spaces. So on underlying topological spaces, they are co-Cartesian. So the topological space of Y is a quotient of the disjoint union of X and Y naught with relation induced by X naught. Okay, and yeah, so this is joined with Gerard Opper, Jack Hall, and Daniel Alpen-Leisner. I'm going to abbreviate here. I don't know, perhaps like this. So it's not yet available, but if you ask me, I can send you a. So there exists a draft that I'm happy to share. Unfortunately, as everything else in these times, it takes forever. But hopefully, at least this year, we'll make it available. So Milnor squares satisfy excision. So I mean the same thing here, right? If you have a functor of some sort, I say that it satisfies excision if this map is mapped to a homotopy pullback. And it satisfies excision for, well, so we have to assume quasi-separated. A mild assumption. But we'll need it. I mean, I would expect that it's false otherwise for quasi-separated algebraic two stacks. So in particular, I mean, or equivalently with this, we could, well, depending on, you know, I mean, it's more or less equivalent, right? So Y is the pushout in the category of algebraic two stacks. I mean, it's a bit not quite true, since I might start with a Milnor square where these are n stacks, and perhaps they're also not quasi-separated. But if these are algebraic two stacks, then satisfying excision for algebraic two stacks just means that Y is really the pushout in the category of algebraic two stacks. And just some remarks here that we can easily. So the question here is local on Y, because if I map to a Z here, Z is a stack for the smooth topology. So and also for the flat topology, I can work locally on Y and assume that Y is affine. So we might as well assume that Y is affine, so that the whole Milnor square is affine. So the problem is not, I mean, it's even for affine squares, it's a question of whether an affine square is a pushout in the category of algebraic stacks. And then, like an example of I mean, I'm mostly working with one stack, but in this case, it's nice that it also works with two stacks. We can actually not prove it for high stacks. We'll explain later what the problem is, but we can do it for two stacks. And one example of a two stack is the Brouwer stack, which, as far as I understand, is the same thing as the second classifying stack of GM and first of Z. Perhaps it's not quite accurate. So this classifies derived Asomai algebras. So it's a little different from the the classical Asama algebra that we also allow shifts, which is why we have this part. And it is also not this problem of Brouwer equals Brouwer prime that you have classically vanish when you consider derived Asama algebras. Yeah, to be precise, I mean, it's only things that are locally. I mean, it's really something like invertible quasi-coherent stacks that locally look like modules over an Asama algebra. But in the case of, let's say, schemes, it's really represented by Asama algebras. So Federico Benda asks here, sorry, can you prove excision also for BR equals Rydh Asama? You mean the classical, where there really are so that's a substack of this thing. Yeah, I'm not sure. I mean, yeah. No, I think no, I think it's right. No, yeah. So this is the Rydh version, but it's not. But you can also talk about really those things that actually come from Rydh Asama algebras. Here I'm talking about really the things that are locally come from Rydh Asama algebra, which is the same thing if you are let's say over a Dream-Mumford stack or over an algebraic space or over a scheme, like Tuan and Lurie has proven. Anyway, yeah. So let me also say a few easy cases of this. Depending on what you think about what you say easy. But the very easiest case would be when, okay, so perhaps I should draw a diagram here. So let's say that we have fixed an algebraic 2 stack. So I'm fixing a diagram, a Milnor square, and then I have some algebraic, let's say an algebraic n stack to begin with, and I'm picking compatible maps, and I want to extend it to a map here. And of course, we know by definition, by this third condition, we have excision for affine schemes. This is exactly saying that we have excision for affine schemes. When locally it's a pullback square of rings, so it maps to Z. So that's a very easiest case where Z is affine. And another easy case is where Z is BGLN, or okay, so this is the same thing as just vector bundles of rank n, and we know back to Milnor that we do have excision for vector bundles. And using these two cases, it's easy to get the case where Z is a quotient by some affine scheme by GLAN. And so you get some quotient stacks, and similarly, we're going to see it soon. But if my Z is not affine by mod GLN, but let's say an algebraic space mod GLN, which is usually called a quotient stack, quotient 1 stack. This then reduces to the case of Z being algebraic space. So if we can do algebraic space, we can do quotient stacks. By the way, it's 60 minutes, right?
That's right. It's 1 hour, David.
Yes, thanks. Right, so let me outline the strategy of the proof. This corner doesn't like me. Yeah, anyway. So the strategy is the following. So we want to, it's kind of similar to this reduction that, I mean, here we are reducing it to a representative case. In general, we don't have a GLN torsor, but we always have a smooth presentation. So pick a smooth presentation in general. I'm going to call this Z prime to Z. And here by presentation, I'm going to choose this to be an affine scheme. So by definition, an algebraic stack admits a smooth presentation, a smooth surjective map from an affine scheme. It might be a disjoint affine schemes, but since I can work locally, these are all now just affine, in particular quasi-compact, so I can just take some open where it's quasi-compact, and then I can pick a single affine scheme mapping surjectively onto C. Right. And what happens is that this is now going to be it's going to be n-1 representable if it's an n stack. And then I pull back. Perhaps I could enumerate this. So pull back to this span, and after having pulled back Z prime, I want to glue or really do excision to get down to something smooth over Y. So perhaps this could be clarified with a picture. I have my x naught x, y naught y. I have my z. The first step, I take a z prime, and I pull this back to x prime naught, and y naught prime. So I'm given maps here, so I can pull back Z prime along these maps, and then I want to descend this to some Y prime here. So I guess this is the step 3 here in pink, and step 2 here in orange, and step 1 in red. And when I've done this, well, then I have since now this is the point about Z prime was that it was affine, and of course I have maps from X prime and Y naught primes. So by this, I would also like here to be such that I get a new Milnor square. So this is the square of the primes. So that's such that this becomes Milnor, which I expect it to be, since if I have a smooth thing here, Milnor squares are going to be they are preserved by flat pullback. So this is supposed to be a Milnor square, and then I get a map from Y prime to Z prime. So that's the 4th step. So since Z prime is affine, I get the map from Y prime to Z. And then finally, by descent, we get a map from from Y to Z. So yes, this is the final step. Step 5. All right, so I mean, all of these steps are very easy except for the gluing step. For this to glue. So this is this is an instance of excision. I'm really talking about excision for the functor smooth, which takes a scheme or a stack to the category of smooth. And in this case, these are going to be smooth n-1 stacks. So perhaps like smooth n-1 here. So if I'm able to glue smooth n-1 stacks, if I have excision for that, I get this. I think there's an arrow missing here, right?
So David, there's another question for you in the chat, if you can see that.
Is there a paper coming out about this soon? Well, yeah, there was from Harry. I think I already sent him the draft of this, but yes, hopefully, as said in the beginning of the talk, I hope it's out before the end of the year. It's more or less done. It's just that there's a pesky error in a very general statement that we have to state a less general statement, and we haven't really decided on how to do that. But everything I say here is proven. Right. Okay. So and there's also there's actually I might say something about this later. Slightly different approach is to, instead of to do this gluing, is to instead, if I have a section here, I get a section here, and I would like to extend this section here, and that would give me maps directly to Z prime here, and then I could just directly use that this is affine and get a map here. And I don't expect to have a map here, but I do have a map here after working locally on Y. So work locally on Y. Then there exists a section of Y naught to Y naught for the Y naught, and then by pullback we get a section of X naught prime to X naught, and then try to extend this section. And again, one can prove that this works in the case when n is equal to 2, but I don't know how to prove this for higher n. All right, so I'm going to mostly focus on the first approach because that also gives a stronger result that you have excision for smooth things, and even more actually. Okay, so back to first approach. Yeah, I don't know what to call this. Well, let's leave this empty. Well, yeah, let me perhaps say pushouts. Oh. So we come to the second result, which is that we do have excision for smooth one. So for the category of ordinary algebraic one stacks over the base, which can take to be affine. But the way that we prove this is giving us even a more general statement. So we don't only prove this, but we really prove that we can construct pushouts. So one way of constructing this is to not think about gluing these maps, but really taking completing this into a Milnor square, and then proving that the resulting map is smooth, which is very easy. So so the question is that a Milnor datum, by which I mean everything except for the pushouts, and I use the same prime notation as we had before. So the conditions here are, as always, that this is a closed immersion. This is affine, and then we also need some cause separatedness. So let's say this is cause separated. I think this is probably enough. But for good measure, why not also assume that this is cause separated? So a Milnor datum of 1 stacks admits a push out and even more when it fits into a Milnor square. I mean that Milnor square is going to be the push out. But it's a bit, I mean, as usual, these things, it's a bit annoying that to prove that Milnor squares are pushouts, you will have to construct Milnor datums. But if, for example, if you want to prove that Milnor square of 1 stacks is a pushout, we only have to prove Milnor excision for 1 stacks, which amounts to proving the existence of Milnor pushouts for 0 stacks and so on. So it's not a vicious loop. But at the end of the day, this Milnor square is going to be a pushout in the category of 1 stacks. Okay, so and how is this proven? Well, it's kind of the same ideas again, that we want to reduce this to the affine case. So what we're going to do here is, now I'm going to write this horizontally to save some space. I'm going to pick I'm starting here. So again, this is the first step in blue here. I start here with an affine and a smooth map. This existence is our algebraic stacks. Then I can pull back this to here, and by assumption, this is also affine. This map is affine. I mean, this map is affine by assumption. But then the question is, can I arrange for something fitting up here? So this is a closed immersion, and these are supposed to be Cartesian maps, Cartesian squares. So this is step 1. This is step 2, and here the difficult thing is step 3. So pick presentation, pull back, and then we need to extend to something which is smooth here, and such that this is affine. And this is the which actually was the starting point. Well, so yeah, so this was a result that we wanted to have, but it's also a nice, very simple question about this extension result. So let me phrase that. So this is what I would call these etale neighborhoods, or perhaps smooth neighborhoods, since I'm here working smoothly. But I mean, the etale case is also nice. So I guess this is theorem 4, that we can find an extension if we are working with one stacks, co-separate one stacks. So yeah, let me keep the same notation here. So this is a closed immersion of algebraic one stacks. And then we have an affine I'm not completely fond with this terminology now, with this notation here, but anyway, smooth, and with, let me call that perhaps G naught with X naught double prime affine. Then there exists an extension G from some affine X double prime to X prime with X double prime affine extending smooth extending G naught. So this is what I mean by smooth neighborhoods. I mean, an interesting case already is when this is affine and this is a stack or even a scheme or algebraic space, and I pick G naught to be an isomorphism. So the mark here is that the identity on X naught when X naught is affine is interesting. And there's also an etale version of this. We could also do an etale and get an etale up here. And there's also a symptomic version with, if you add some minor assumptions. So as an example here, we could take if I have a pair here as above with X naught prime affine admits a Henselization. Like X prime can Henselize along this, and it's also which is affine. And I can see that I can, if I have an affine closed subscheme or often space or a stack, I can find an etale affine neighborhood, and then pass the Henselization of that thing. So this is something that was not even known for schemes before. So even when X prime is a scheme. Right, but let's talk about the proof of this and mention where really that I'm using one stacks here comes into play.
Maybe first, David, before you start the question.
Yes, is there any hope to relax the assumption that X double B0 is affine? Yes, so I mean, what I usually am doing is working with this local or smooth neighbors of stacks where also this thing is a stack. That's a very interesting case where, like, if this is a general stack, you could make here a stack which is a quotient stack, like affine mod a linear reductive group, etc. So if this is a stack with which is cohomologically affine, so as linear reductive stabilizers, close points, etc., then it does work with more work, but it is possible. But if you don't make this affine, but I mean, we will see in the proof, even the first step breaks down. yeah, so first, just a necessary introduction step to find a type over the integers or over a field if you're working in eco-characteristic. But then we want to use deformation theory to get different infinitesimal solutions to this problem. So, and here the obstructions. Let me first state what we get. We get x bis n. Yeah, I can draw them horizontally, perhaps. Smooth. So these are the GNs extending. G naught, and here, I mean, the obstruction here lies. Let's see here. Lies in H2 of x is 0 for the cotangent complex. Now this is a smooth one. Okay, so it's not just over x not prime dual and then tensor sum. Yeah, something like in mod in plus 1. Or press in plus 1 or in plus 2. And the thing here is that this thing is, due to smoothness, this is concentrated in cohomologically degree higher than, lower than 0. This is taking a dual. So this vanishes since it's affine. But if you relax the affineness of this, then you can certainly find obstructions here, so that you cannot extend your thing. So, but the important is that x naught base is affine. All right, I think I'm soon running out of time, but there's 2 more steps here, and this is the pesky step. Which is solved by Tanaka duality to get a map from like a G hat from the completion here. Now we're getting very confused here. Yes, sorry, yes. This is right. No, I'm right. Yes. The problem here is that you can always form this one, right? This is just these are affine schemes. So this is the spec of the inverse limit of the rings of these things, and I have maps here to here, but I don't have a map from spec of this complete ring to not to x hat, but even to, I want to make it to x, and it's not going to be smooth. It's going to be formally smooth. What I'm using here is that I want that a map from this completion to x is the same thing as a system of maps from these infinitesimal truncations. So I want this to be an I guess an equivalence of, let's say, infinity categories, but really like yeah, in the case of one stacks, it's just group points. Let's say infinity group points. And this, I only know how to do this. So this is true for n equals 1 by Tanaka duality. Because, I mean, here what we have proven is that that maps from any scheme, let me call that Z, into X is the same thing as tensor functors, co-continuous tensor functors from quasi-coherent sheaves on X to quasi-coherent sheaves on Z. But this is only valid for one stacks. And then the knowledge that coherent sheaves on the completion are just limits of coherent sheaves on the truncations. So it's a roundabout way of proving that this is the direct limit of these truncations in the category of one stacks. And I would really expect that this holds in more generality. I'll can mention it later. There's also a question here, reduction to finite type. Well, yes, you did need some absolute approximation results, which would then also only be, I guess this would also only work for one stacks. But the case it's very easy, because I mean here I can assume that in the application that we need here, no, they are really, they're not affine. Okay. Let me just write down the third step here. Last step here is now to use Artin algebraization to get from the formal case to the algebraic case. So I can approximate this formally smooth solution to honestly smooth thing, still keeping this affine. But yeah, and let me just finish with this remark that if x naught is a point, then we get the requested, let's say this star, the star holds for n stacks, for high n. But I don't know for all n. I don't know how to prove this except by going through this Tanaka duality route, where we consider the categories, or the monoidal categories of coarse-grained sheaves. And I also might expect that this shouldn't hold for higher stacks, in that this shouldn't have enough information to capture like two stacks. One would rather here have to replace this monoidal category with perhaps say the infinity category of quasi-coherent stacks, like in the Asumaya algebra situation. And then you could perhaps treat two stacks, but then you would like to treat three stacks, and you would have to go up in this hierarchy. I think there should be some nicer way of doing this without passing to using Tanaka duality and passing here. Okay, sorry for going a few minutes over time.
No problem at all. Thanks a lot, David, for a nice talk. Now, everybody can unmute, and we can give David a round of applause. Okay, great. Then we can maybe start preparing some questions from the audience. There was a question in the chat. Maybe you answered it already. You did.
I hope so.
Right, I think you answered the question in the chat.
Yeah, but yeah. So there's here. I mean, this uses really like absolute Noetherian approximation, which also works for all one stacks. But here I have no idea about higher stacks here. But and I mean, personally, I'm not so interested in higher stacks, but I still find it kind of annoying this thing that seems very natural to hold, and you can prove it for as soon as you have a point. And not like it's just only the problem is that when you have this. I mean, this thing is really spec like A, where A is I-adic and I is not maximal. That's the problem. I can treat the case where it's maximal. Which kind of descent result you have this for the stack of Rydh asymptotic algebras? Yeah, so I mean, I'm not an expert in this. I might get this wrong, but as far as I understand, I mean, so here so this is kind of the BR here. By this I mean, so this is the stack of, let's see here. I think this is supposed to be invertible quasi-coherent stacks over X, and which is the same thing as locally the quasi-coherent sheaves of on the GM-gerb corresponding to an asymptotic algebra, or to a derived asymptotic algebra, something like this. So if you look in, I mean, like paper of Twen and Antio Gettner, table explains much better, and it's known that this is really honestly globally given by a derived asymptotic algebra if you are on a scheme or more general algebraic space, or even a Dillingen-Mumford stack. But there was also this question, well, if we just work with the substack of those really coming from derived asymptotic algebras, if you do have excision for that, and I don't know if that's the case. I would expect that it's not, but I don't know.
Okay, feel free to ask your questions.
So I missed the first half of the talk. Is there any way you could email me these notes?
Absolutely. So
thank you.
What, was it Harry or?
Yeah, that was me.
Yeah.
Yeah,
Send it to anyone who asks.
If David agrees, we can put the notes online for the seminar, the web page of the seminar as well.
So if you work with derived stacks, but still one stacks, like derived one stacks,
right,
then most of these results still
generalize. So that's already written in the paper from let's say like this statement. So derived, you can also replace this with as I also mentioned, like symptomic or quasi-smooth. Not necessarily flat in the derived case, even though you need a tiny bit of assumptions if you want to do quasi-smooth. But if you just want to do smooth, you can allow this to be derived. That's okay. It's a fairly easy reduction in where you can first prove it for the classical truncation, and then you can use deformation theory to lift the solution to the derived level. So it's a very simple argument. The derived argument for the quasi-smooth case is more involved, but it's similar to the symptomic case.
Okay, and you would still only need cohomological affineness of this X0 double prime.
Right, and there's a bunch of annoying things in mixed characteristic. One has to be a little bit careful. Like if you have only a finite number of characteristics, never a problem. But if you have all characteristics and like the points in characteristic 0 is not a dense open, and so then you get problems when you work with cohomological affine stacks for a number of different reasons. But like in pure characteristic, or when you have finite number of characteristics, you can work with cohomological affine stacks. Yeah, they should also have the resolution property. So think of affine being replaced with like affine mod a linear inductor group, then it's fine.
I guess for the resolution property, you might even need some slightly stronger condition on the group, right? Like some embeddable.
Right, it should be an embeddable, it should embed
Okay.
into GLAN.
Okay. Yeah, but that's all I need for my application anyway. So.
But for this kind of Milnor excision type of results, you don't it never enters having stacks there.
Okay, are there any more questions?
Yeah, I've got one. So the excision result, is it known for just when all of the things are affine except for the target? So like, you know, if you have some n stack, and then you've got a ferron push out of affines, is it known for the target being any n stacks, mapping into
No,
an n
I mean,
stack?
as I said, it's really, this is really local on Y, so I can immediately assume that this is affine. So the problem is this might just be an affine square, but it's nice to do it this way, because when I did the pushouts, that thing really becomes a pushout due to this being true also when these are stacks. But all the difficulty lies in the affine case.
Okay, cool.
So that's why it's really like the classical Milnor excision with rings and with the category being maps into Z.
Thanks.
And I'm sorry, I mean, I missed this result by Morrow and Krishna and so on. And I guess there's also a result on CDH descent using different methods than pro-excision by a large number of authors.
Right. Any more questions or comments? Last chance. Okay, that seems to be the case. Then let me thank all the participants for attending the talk, and let's thank David again for a very nice talk.